Welcome to EDU World Space.
So for part A, we're going to relate the conditions inside of the rocket and outside of the exit orifice. We're going to apply the equation and the equation of continuity. And so we can say P sub inside the rocket, P sub in, plus 1/2 times rho V sub in squared would be plus rho G Y sub in. This would be equal to P out, or just outside the exit orifice, plus 1/2 times rho V out squared plus rho G Y out. And we can then say that the pressure P plus 1/2 times rho V sub in squared plus, this would equal the atmospheric pressure P naught plus 1/2 times rho V out squared. And so we can say then that 2 times the change in the pressure divided by the density rho would be equaling V out squared minus V in squared. And so we can say that 2 times the change in the pressure divided by rho would be equaling V out squared. And then we apply the equation of continuity. So this would become 1 minus V in over V out squared. After this step, then we apply the equation of continuity, where here A in V in equals A out V out, because we want to substitute. And so we can say then that the area times V in would be equal to the area naught times V out. And we can say that then V sub in over V out is equaling A naught over A. This ratio is much, much less than 1. And so we can now say that then, because of this, 2 times P minus P naught over the density rho, this is going to be approximately equal to V out squared, because we know that this ratio is much less than 1, which is essentially canceling out this term here. And so we can then solve for V out, which would essentially just equal V. This would be equal to the square root of 2 times the change in pressure divided by the density rho. This would be our answer for part A. And then for part B, thrust is defined in section 10, and we know that the formula for the thrust would be equaling the relative times dm over dt. So here, it's essentially interpreted as on the rocket due to the ejection of mass. And so this would be equaling V out multiplied by the density rho times the change in volume with respect to time, or the volumetric flow rate. And so this would be equaling V out times rho, and then for the volumetric flow rate, we simply use the formula V out over the cross-sectional area just outside the exit orifice. And so we can say then that the force of the thrust is equaling rho V squared A naught. And so this would be equaling rho times 2 times the change in pressure divided by the density rho. They, of course, cancel out, multiplied by the cross-sectional area. And so we can say that then the force of the thrust would be equaling 2 times the pressure minus 2 times the change in pressure times the cross-sectional area just outside the exit orifice. This would be our final answer for part B. That is the end of the solution. Thank you for watching.